All right, ladies and gentlemen, class recording has started. So today, I want to review some of the topics that we talked about the other day, impulse and momentum, make sure we understand those things, look at some calculations, apply them a little bit more, talk about some of the things behind it, explain the egg demonstration that we did yesterday at the end of class, and then also talk about your lab a little bit, which is a little ambitious for the time we have right now, but we'll see how it goes. So, all right, first things first. On the sheet that I gave you, the one that says momentum, impulse, momentum topics, or whatever it says there, okay? You have a chart up at the top there, okay? And it asks you to rank those four things, or it says which one has the greatest momentum, all right? Let's do this first. To start, you'll see I kind of added 2 rows to this table. You don't have the space to do that, but maybe you'll find some way to figure it out, all right? And for starters, let's calculate the momentum of each of these things, right? There's no more back there? Here. All right, good with these 4. All right. So the one on the right has the biggest momentum. All right. Now, a parallel that people try to make, and because they sound, oh, well, sorry. We calculate momentum like that, right? Mass times velocity. Okay. All right. Sometimes people try and make a parallel between momentum and kinetic energy because they both depend on mass and speed, right? So, if we take a look at the kinetic energy, right, it might tell us a different story. Because we said one of the factors in kinetic energy we talked about was that the velocity being squared, right, that's an important factor when we're determining the kinetic energy, yes? Okay. But if you look at the momentum, here, actually the slowest moving object has the greatest momentum because those factors of mass and velocity are more evenly balanced, right? So it's the slowest moving object, but it's by far the heaviest object, right? If we take and calculate the kinetic energies, we might see a different story. So why don't you do that real quick and calculate the kinetic energies of these objects quickly, please. Yeah, I said I know that I made this chart here on mine. Did I do those right in my head? Anybody? All right, good with those 4 numbers? So, in momentum, right, the slowest object actually had the most momentum, but when we do kinetic energy and we have to square the velocity, right, actually the lightest object has the greatest kinetic energy. Why? Because its speed is the greatest, and by squaring speed, it affects that more, right? So while both of these things depend on mass and velocity, we have to make sure we keep them straight. Next week, when we get into collisions, and then the first week of December, when we start actually analyzing those collisions, next week you'll do the lab. Following week, we'll do some analysis and questions and stuff like that. We'll see that we'll have to actually analyze both of these things to get a full picture of what's going on when we interact 2 objects. Okay? Good there? All right, next question. What I think is actually question number 4 on your sheet, I think. Oh, hold on. There it is, yep. It says, consider 2 objects moving at constant velocities in opposite directions. Object A has a mass of 20 kilograms, is moving 5 meters per second to the right. Object B has a mass of 10 kilograms and is moving 10 meters per second to the left. These two objects have exactly the same momentum. True or false? Formulate yourself an answer. 15 seconds.
Are we doing classes 7, 8, 2?
Eventually, yes. So yeah, you got a lot of space. You got a lot of space at the bottom, but so I didn't space these out very well. I'm sorry. So, you tell me. Is momentum a vector quantity?
Oh yeah, James.
So the correct answer here is false, because momentum is a vector quantity. So even though these two things, when you multiply their mass and velocities, have the same magnitude of the momentum, it is not the same momentum because of the vector nature of momentum. All right? Good there? All right. That leads us to this question right here, which is actually in your packet from the first day. All right? Conceptual example 7.5. I think it's on the 3rd page of your packet. It's a lady standing in the rain holding an umbrella. All right, so it says, a person stands under an umbrella during a rain shower. A few minutes later, the raindrops turn to hail, though the number of drops hitting the umbrella and their speed remains the same. Is the force required to hold the umbrella upright in the hail greater than, less than, or equal to the force required to hold it in the rain? Well, you can probably tell by the picture what's the answer probably supposed to be. Okay? Probably greater than, all right? But let's talk about why. In the rain picture, right, this raindrop falls from the sky, hits the umbrella, and then rolls gently off the edge like that. Okay? But in the hail picture, this hail falls from the sky, hits the umbrella. If it fell from the same height as the raindrop, theoretically, what should the velocities be when it hits the umbrella? Same, right? Gravity accelerates all objects, blah, blah, blah. But in reality, that might not be the same because of terminal velocity and the shape of the objects and things like that, but let's not worry about that right now. Okay, let's say that they're going the same speed because that's what it says in the problem. What does the hail do, though, when it hits the umbrella? It bounces, right? So it was going down, now it's going up, and eventually it comes back down, but that interaction with the umbrella involves a bouncing, whereas the rain just hits the umbrella and rolls off the side. We talked about this on a couple different occasions, right? Bouncing is a greater change in momentum than anything. Why? Well, what sign would the velocity have of the hail drop when it hits the umbrella? Let's call it, well, it's going downwards, so yeah, it doesn't really matter. Doesn't really matter, but let's call it negative because it's going downward. But then when it leaves the umbrella, it's going which way? Positive. It might not be exactly the same speed, right? But still, going from a negative number to a positive number would be a bigger change than the rain, which is negative. Then it hits the umbrella, it slows down, but it's still going negative. That's not quite as big of a change, right? Does that make sense? So in here, the change in momentum of the hail is greater than, oh, I should do this. Okay, let's do this. The change in momentum of the hail is greater than the change in momentum of the rain. Does that make sense? But does that answer our question? What did the question ask us about? How much force, right? The question is asking us about force. Before we answer that question, I want to go back to the sheet that we were working on before, and I want you guys to answer these two questions. Question number 1. A moving object, or an object moving with constant velocity has a constant momentum, and an object moving with constant velocity has a constant impulse. Both of those are true or false questions. So question number 1 and question number 3. Guys, do this. Talk to the person next to you for 30 seconds. Come up with answers to these questions. Go. Alright, so let's discuss. First, object moving at constant velocity has constant momentum. We talked about here, that's how we calculate momentum, right? If the velocity is constant, the mass doesn't change, constant momentum. But, what did we say our definition of impulse is? So, first, how do we calculate the impulse? Force times time. But, as far as a definition goes, what does impulse do to an object? It changes the momentum. Impulse changes momentum. And we refer to that as the impulse momentum theorem. An object moving with a constant velocity, is its momentum changing? No. So does it have impulse? What would be the impulse of an object moving with a constant velocity? 0, right? I suppose you could make the argument that if it's moving with a constant velocity, it continually has a 0 impulse, right? And you could make that argument, but more accurately, we should say that the impulse is 0, okay? But more importantly to this discussion, right, that whole impulse momentum theorem, right? That impulse causes a change in momentum. That being the case, going back to this discussion right here, which requires a greater impulse, the hail or the rain? The hail requires a greater impulse because impulse of the hail has to be greater than the impulse of the rain. Why? Because impulse changes momentum. And if the hail has a greater change in momentum, it's also going to have a greater impulse. We just discussed that impulse depends on force and time. Right? Now, we don't know for sure, because we don't really know the time, right? But if we had to take a guess, which one's probably going to require the greater force? The hail, because it requires the greater impulse. Okay? Good there? Questions? All right, let's put some numbers on it. These 3 questions right here. It says an SUV with a mass of 2,200 kilograms is traveling at 26.11 meters per second, which is around 60 miles per hour. So it says, applying the brakes gently, the vehicle comes to a stop in 21 seconds. How much force is applied to the SUV by the brakes in this instance? I'm just going to do the first one here real quick because these calculations are basically exactly the same. Is the momentum of this SUV changing in this problem? Well, what's it doing at the beginning of the problem? Traveling 60 miles per hour. What is it doing at the end of the problem? Stops. So is there a change in momentum of this in this problem? Yes. And if there's a change in momentum, there has to be impulse. All right? Now, let's be a little more detailed. We just discussed impulse depends on 2 factors, right? What are the 2 factors? Force and time. There is a change in momentum. Momentum depends on 2 factors, right? Mass and velocity. Which one of those factors is changing in this problem? The velocity. The mass of the object doesn't change, so we can make the right-hand side of the equation look like this. Then, if we wanted to, we could expand it out a little bit more, because that's always what delta is, right? It asks us to solve for the force, and that means we need to know all the other things in that equation. Do we know the time? Do we know the mass? Final velocity is always going to be what? 0, and then the initial velocity, 26.11. So let's solve for the force that is applied to the SUV in this problem. Alright, did we end up with that? Negative 2735? First, is it okay that it's negative? Yeah. What force is probably causing the car to stop here? Friction, right? And friction always acts opposite of stuff. Okay, so that's alright. Alright, good there. Okay, next problem, number 6. Very similar. The only thing that changes in that problem is going to be what? The time, right? So we're still going to use this equation right here. The right-hand side doesn't change at all, right? It's still the same SUV with the same mass. It's still ending up at 0. It still started at 26.11. The only thing that changes there is the time. So go ahead and figure out the force for that one. And if you want to, do number 7 as well, right? So. Not if you want to, do number 7. Well, I suppose it's always if you want to. Yes? For red or for blue? Red? Okay. This is 2200, Joe, right? And then initial velocity. Did you put in 60 or did you put in 26.11? Multiply those two together, right? And divide by 21. Do it again.
You're supposed to subtract the before you multiply it.
But the V final in this case is 0. So, yeah. Okay. Oh. Inside or outside? Yeah. Okay. If you need to go to the restroom, feel free. All right. So, are we okay with these numbers here? All right. These 3 problems here illustrate an important application of the impulse momentum theorem. Impulse momentum theorem, right? Impulse is equal to the change in momentum. This case in particular, the change in momentum in every situation was exactly the same, right? Because what was happening in all 3 of these situations? Well, what's happening to the car in all 3 of those situations? It's braking and eventually it does what? It stops, right? Eventually it stops. A couple of different ways, but eventually it stops. And that means that the change in momentum of the SUV in every problem was exactly the same. And that means that the impulse in every problem is also exactly the same. But impulse depends on two factors, right? Those two factors being time and force. When we have a situation where we are always applying the same impulse to an object, we can go about doing it in two separate ways, right? In the first problem, the force was much smaller than the other two problems. Why? Because look at the time, right? How does the time in the first problem compare to the other times? It's the longest time, and that requires the smallest force. Number 7 is exactly the opposite, right? Shortest time, biggest force. What kind of relationship are we seeing here between force and time? Inverse relationship. But we will only see that inverse relationship if the momentum change is the same in each situation, right? Here's a picture from the very back page of your packet, but it also is the demonstration we did in class yesterday, right? You drop an egg from the same height, or 2 eggs from the same height. When they reach here, how fast are they going to be going? The same. And then, here I should do this. When they reach here, they're going exactly the same speed. Gravity accelerates all objects the same, right? Then, from this point onward, eventually what happens to both of those eggs? They stop. So the change in momentum from here, to here is exactly the same for both of them. How long does it take the egg to stop when it hits the plate? Long or short? Real short time. Making it fall into this pillowy cushion, right? It starts slowing down the moment it hits the surface, but because the pillow bends or cushions as the egg falls into it, the time that it takes for that egg to stop is much longer here than it is here. Longer time requires what? Lesser force, right? That's why we can throw the egg into the bed sheet as much as we want to, or as fast as we want to. I guess not as fast as we want to. But that's why it doesn't break when we throw it really hard into the bed sheet. The bed sheet does exactly the same thing as the pillow does, right? It cushions and it moves with the egg, and it increases the time that it takes for that object to slow down. Okay? Does that make sense? All right? We talked about that same concept, Hannah, when we talked about catching the baseball, but in that case, in the last unit, we were talking about work, right? Work depends on two factors as well, right? Except instead of force and time, it's force and distance. So generally speaking, increasing the distance is also going to increase the time over which you do that work, right? And we talked about it in the same context of catching a water balloon or catching an egg at the egg toss or whatever. Very similar ideas, as long, in that case though, we had to say that the amount of work was the same in both cases, right? The water balloon, whether you catch it by using the cradle or whether you catch it with your hands flat out, has kinetic energy before it hits your hands. It doesn't have kinetic energy when it stops. Same idea, right? As long as the work is the same, we'll see that inverse relationship between force and distance. As long as the impulse is the same, we'll see the same relationship between force and time. Okay? And that leads us to this problem. Right? Number 8. What does an airbag do for you?
Oh, it gives you more time to stop.
Increases the time that it takes for you to stop. If you're in a car accident, you're moving at the same speed as the car is, right? Initially, you and the car move at the same speed. When you get into a car accident, that car feels a force from the guardrail, the telephone pole, or another car, right? And so the car experiences an acceleration. But what do? You keep going. Why? Inertia. But eventually, what's going to happen to you? You're going to stop, right? You either stop when you run into the cushy airbag that increases the time it takes for you to stop, or you stop by hitting the steering wheel, right? That's not good. Seatbelt does the same thing, right? But see this is kind of a not true, but it still increases the time because it doesn't lock right away. You know what I'm saying? Like it takes a small fraction of a second for it to lock. Okay, but also too, your arms and your legs kind of keep moving, but it kind of keeps the middle of you there, right? So that sort of increases the time as well. Like it doesn't all stop you at once, you know? So yeah, it does the same thing. But if you've ever seen anybody who's been in a car accident with an airbag deployment or has been like, with a seatbelt, it's not that it doesn't injure you at all. A lot of times, people who have seatbelt or are in crashes, they'll have like burns like across your chest, or like if they run into the airbag, they'll have like cuts on their face or stuff like that. So it's not like it's no force, right? But by increasing the time it takes for it to happen, it decreases the force. It still it has to stop you from, like, it has to apply a force to stop you, right? And if you run into it like straight on, Hannah said, how do you get cuts from the airbag? If you run into it straight on, okay, fine. But a lot of times if you're like twisting or something like that, it'll like scrape you, and it's just like scraping your arm against like on the carpet or something like that, It gives you basically like a rug burn. But a rug burn is better than giving you a massive concussion, right? Where your brain runs into your...
It's like your airbag is, but you're already locked down by the seatbelt. You don't even hit the airbag.
You do.
Your seatbelt doesn't lock if you go all the way out.
So, well, it does lock. It does lock in when. Yeah, it's got a little mechanism in it, like where.
I want to lean in to like look at cars. It always locks me, like chokes me, and like it's like that. It locks so.
Wear it
hard.
anyway. So, Evan, it's got a little like mechanism in it. So the seatbelt's on like a pulley, kind of like it's on a roll, and when you pull it out it unrolls, and when you pull it back it rolls. But there's a mechanism that kind of swings freely, and it's not connected to the roll, so the roll can like twist and turn like this. But when you slam on the brakes, the inertia of this thing goes forward, and it prevents the seatbelt from unrolling anymore. Does that make sense? That's how the seatbelt works. That's why it rolls and unrolls when you're not, or when you're not accelerating. Because when you're going at constant velocity on the highway, you can still move your seatbelt all you want. But when you're accelerating, this thing goes forward. It actually doesn't go forward. It just stays, like inertia takes it forward as the rest of the car slows down, and that prevents the mechanism from turning anymore. And that's why it locks in place like that. But eventually, the same thing is increasing the time, right? So this same instance is what causes a concussion. Concussions are like big time, big in the news right now. Yeah. A concussion, well, because like with sports and things like that, there's lots of concern over kids and adults getting concussions.
Now that is
Because at the time, we knew what concussions were, but now as we study them more and more, we realize the long-term effects of them. Right? A concussion is basically a bruise on your brain. That's pretty much what it is. But, if we talk about your head, right, I'll use this color so it kind of looks like, so. Do you want that to be your brain or your skull? Okay.
That's the brain.
That's brain, okay. There's your brain, all right? And then I'll use gray, right? So, right, there's your skull, okay? So, if you get hit, so a concussion happens, right? You're moving, right? And then somebody hits you in the head, or you hit the ground, or something like that, right? So as you're moving, your brain and your skull are all good, right? They move together. But when you get hit on the head, or when you hit the ground with your head or your skull feels a force, right? We'll call this the ground. I know that's not where the ground usually is, but rotate it 90 degrees, okay? Your skull feels a force, so it stops. But what does your brain do? Your brain keeps going, right? Oh,
Your brain is not connected to your skull.
your brain is not connected to your skull.
How does it stay there?
It doesn't. It moves around.
So wiggle?
There's a little bit of fluid between your brain and your skull, and so your brain is not connected to your skull.
Fluid? What fluid?
Say again? Yeah, you have like a sac, and then there's fluid in there. But you think so? But that's also though when. So basically, what happens, right? Your brain keeps moving forward, right? Here. So if you join pre-med club, you'll know this. Right? Boom. Right? And that's basically what happens in a concussion, and you end up getting a bruise on your brain. And the more severe the bruise, the more severe concussion. Right? But wearing a helmet, right? It doesn't really do a whole lot because the same thing still happens. A helmet is there more to prevent a fracture to your skull than it is to prevent a concussion. Because a helmet provides some cushioning for your skull, and it slows down the rate at which your skull hits the ground, but you can't really slow down the rate that your brain hits your skull, right? All right, tomorrow we'll talk a little bit about your lab, because these ideas are in play in your lab, and then we'll talk about conservation of momentum.